Imagine, if you will, a detective. You don't know why, but he's been searching for flatness, for a vast expanse of perfectly flat ground. And he wakes up. He doesn't know how long he's been asleep for, but he finds himself in that land of flatness. And being a detective, he goes out to explore. And the exploration confirms flatness, smooth, perfect flatness. But it's dark, and he only has his feet to guide him. And he continues. And he finds himself going up a hill. A hill in this flatness. He reaches the top of the hill. It's not a huge hill, but it's not flat. But then he tumbled off that hill, not into a valley, but into a crevasse. Why is there a crevasse in this flatness? He claws his way out, and on the other side is flatness. He's perplexed. And from nowhere, an old man with a beard approaches him, and he says, "Young detective, there are two types of antenna designers. There are those who know they are designing antennas, and then there are those who do not." Of course, what I'm talking to you today about is this shocking frequency response. I've been working over the past couple of months on and off on this device here. It's supposed to be just between these 2 points here. 1 gigahertz of bandwidth plus, well, 1 gigahertz would be nice. Completely flat response. Now, of course, there's no reason to have a 1 gigahertz bandwidth analog video circuit. Highest bandwidth that you can get in sort of commercial devices is 145 megahertz. But why not? The chips should be able to do it. I have a 1.7 gigahertz op amp here, 1 gigahertz OTA, 1.1 gigahertz rated switch. This thing should be flat to 1 gigahertz, but it's not. I'm going to share with you why. It was an interesting story. So, there are two problems with this circuit and two interesting tales to share. So I thought I'd make a quick video on Halloween to share them with you. So the first story is the valley, this big dip, this minus 25 dB loss at 500 megahertz. It was odd that it was exactly at 500 megahertz, and it took me a while to find out what the problem was. You see, the way I go about building out these circuits is I design them, typically iterating on previous designs. I design them, get the boards made, then start populating components and sort of testing as I go. So down here we have our power supply, and up here is sort of the path, the signal path from the input to the output. And I populated the op amp, and that's the only thing I really needed to get a signal through here. And I found, as soon as I connected to the VNA, two things. I found the big hump and this big valley at 500 megahertz. I started with the valley because the hump was about 9 dB. Where my zero reference wasn't exactly right, but it was still a big peak at 350 megahertz, but the 500 megahertz valley of 25 dB was pretty concerning. And it took me a while to find out what the problem was. I was so concentrating on this part of the board that I forgot that I had a long trace coming out of this op amp, so actually coming out of the input of the op amp, not even in the feedback path, just branching off from the termination resistor here, traveling down here about 5 centimeters roughly, and just going to nowhere. And I basically created sort of an RF stub. This is where you get into the weird world of wires not being wires. And that stub was open-ended on one end, and it was acting like an open circuit antenna, and was reflecting back and absorbing this notch at 500 megahertz. As soon as I connected a resistor here and connected it down to the little components down here, that path was complete. There was a path to ground. 500 megahertz notch completely disappeared. that is sort of one of the perils of testing components one at a time. I was so concentrating when I was designing this board on the layout around here. This op amp is an LMH6702. The op amp has a lot of very, very specific guidelines for how the board should be laid out to get optimal performance. It talks about using the SOT23 package versus the SOIC, which is like that sort of size. Because the smaller one has lower loop impedance, it talks about clearing out the ground plane, putting the feedback path resistors on the back of the board to again minimize the inductance. Talked about having star grounding for the decoupling capacitors. I did all of that, and because the main signal path is going this way, and I had this other trace going off here that I completely forgot about. It's never been an issue when I've been working at sort of sub 150 megahertz, having traces like that. But in this case, it bit me in the butt at 500 megahertz. So once I started populating this, I realized what the problem was, and that problem went away. Now, I have another path, another component in the signal path here. This is a 1.1 gigahertz switch. That 1.1 gigahertz switch I've used plenty of times before and never had issues with it. I appreciated the fact that it had a very high bandwidth. It's designed for sort of XVGA signals at like 120 hertz frame rate. So that's why they need that bandwidth. But one thing I didn't consider was that it has a relatively high input capacitance. An electronics engineer at work was looking through the data sheet of this as I was explaining my problem. He said, "Hey, do you know this has 12 puff of capacitance?" And I hadn't thought about that before. It had never really been an issue before. And so it turns out that sort of combination of the signal path, the 12 puff of capacitance there, appears to be what's behind this 350 megahertz peak that's ruining my field of flatness, if you will. It's hard to sort of test whether that's the case. Like I've tried removing that chip and using test points up here, but of course sort of test points like this on a jumper, even with a custom made sort of BNC cable going to here, it's really hard to get a good reading. That's one of the challenges of working at these sort of frequencies, is you have to spin a board or do some pretty precise prototyping to actually work out what's really going on. You can't just sort of breadboard these. That brings me to sort of an interesting story. This board, I'll get into in another video what it's all about, but it's actually a similar design to something I've done in the past, operating at sort of 50 megahertz. And in that circuit, I had an op amp before and after the switch. And I wasn't sure when I designed that circuit why I put two op amps in there. I was sort of working on, not on breadboards, but on proto boards, which is sort of fine to 50 megahertz. But I found that it was important to have an op amp after the switch, because what I was doing, and I went back and looked at the schematic for that, which is written on paper. I didn't do it on CAD. I had like a 1K resistor from the first op amp going into the switch, which basically isolated the capacitance from the sort of loading down the output of that op amp. Then I had another op amp on the output of that switch, which then took it to 75 ohms, which is the impedance, output impedance that I want on here. And when I was designing this board, I looked back at my old schematic and was like, I was kind of breadboarding this or proto-boarding this. There were lots of loose wires all over the place. And I wasn't quite sure really why I needed that second op amp, but I knew that when I was building it out on the breadboard, that putting that second op amp in there fixed it. And I thought, you know what, there's probably no reason for to do it. I'm designing this properly. I don't need that second op amp. I've got already 250 odd components on this board. Each of these op amps requires like 5 decoupling caps and a bunch of resistors and other things. If I can save adding a bunch of op amps, why not do that? So I didn't include them here. But that's meant that I'm loading down the output here with this 12 puff, which is not doing great things to the frequency response. So what I'm at now is I've got a relatively flat frequency response. I've got a bit of a hump at 350 megahertz. It's not going to be a problem for my use case. I'm using this with HD video at 1080p, 60 frames a second. That's like lower than 150 megahertz or roughly 150 megahertz. It'll be fine there. But I sort of wanted to give myself a challenge in designing this board, and I wanted to reach sort of a gigahertz of bandwidth. I haven't quite got there. The performance is actually quite good after 350 megahertz. It's flat all the way out to a gigahertz, so that's nice. There are ways you can deal with this loading capacitance. You can put another capacitor in the feedback path, but that'll ruin the bandwidth, but it'll tame down that bump. I'm going to leave it as is, but in my next rev of this board, I'm going to do the 2 op amps, have a high value, well, relatively high value, like 1K or maybe even 100 ohms is probably fine, resistor on the output of this before it goes to the switch, and have another op amp on the side output of this switch. Potentially I could find a switch that has lower capacitance, but anyway, I just wanted to share with you what I've been doing this Halloween. Hopefully everyone's having a safe but spooky night, and I'll see you all on the next one. Bye.